Welcome to my new calculus channel. My name is John Gabriel. And in part 11 of this series called What Your Ignorant Teachers Could Not Tell You, I continue the discussion on how you got the decimal number system and radix systems in general. So if you recall, in the last episode, I showed you how to convert even fractional parts into other bases. I didn't waste time or show you how to convert whole numbers into different bases because that's fairly easy. So in this video, what I'd like to do is talk more about the mainstream ideas, the flawed mainstream ideas, and how you got your mathematics today and your understanding of those imaginary mathematical objects called real numbers. There is no such thing as a real number, not even any rational number. And I'm going to talk to you a little more about two particular individuals who tried to construct an object that represents a real number, and they're namely Dedekind and Cauchy. But before I start with them, I'll explain a little more background to the concept of a limit and how we got it. So let's begin. Now, in high school, you are shown how to derive the series for a sum to n terms, for the sum of a geometric series to n terms. And now, as you all know, geometric series converges. So you're normally told, write down the series like this to n terms. Okay, so if it's Sn, then the first term is r, and the second term is ar plus ar squared, all the way up to ar to the n minus 1. n minus 1 because you started with a, right? And of course, you could take the a out here and just write that as 1 plus r. It makes it easier to work with, like that. And then in order to find a formulation or a formula for the sum and get rid of the terms in the middle, you multiply both sides by the common ratio, right? So you'll have a into r plus r squared plus, and this one here would be plus r n minus 1 plus r to the n, right? Okay, and so then what you do is you subtract the two equations. So you can subtract 2 from 1, and if you do that, what you'll get is Sn 1 minus r, like that, is equal to, let's see, 1 minus Rn, right? Yeah, and so of course, 1 minus Rn times a, which is the first term, and then you'll have that Sn is equal to a 1 minus Rn over 1 minus r. Okay, so that's the way you derive the sum to n terms. Now, the problem with mainstream academics is that they never really understood these things. And I'll explain to you why they didn't, because Euler, who is the chief root of all the problems, decided that he would do the following. He separated these two, as you'll see here, as, oops, that's not an addition sign, it's a subtraction sign. He separated them like that, and then he considered what happened to this whole thing as n became indefinitely big. So in other words, as n becomes indefinitely large, and this does not mean infinity, it just means it increases without bound. Since r lies between 1 and minus, r lies between 1 and minus 1, it follows that this expression here would approach the value 0. It never gets to 0 because n can never be large enough so that this here evaluates to 0. So it's very clear that Sn is actually a limit, and this is the limit, okay? A over 1 minus r is the limit of that convergent sequence. And so the primates in the Church of Academia, or mainstream academia, my intellectual inferiors, decided that it was possible and that it was a good idea to simply just go ahead and assign a geometric series the value of its limit, interpreting it as an infinite sum. In other words, the morons decided that S infinity is that, okay? As you can see, the value of n doesn't even play a part in here anymore, okay? So n is gone. It's assumed that n is so big, and this series here, this term here just disappears, okay? The problem is this term here never disappears, and this expression here never reaches the limit, okay? Never. It's not possible. So if you have a half plus a quarter plus an eighth plus dot, 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 you can't sum this to infinity, okay? Because that would be an infinite task or a super task. It's not possible, okay? So, and always you'll still have this leftover part here, which means that no matter how far you could sum, this part here would prevent it from being the same as the limit, because in actual fact, it's subtracted from the limit, and this here is the limit, okay? This here is the limit. So this part here gets subtracted. Now, you can say, well, all the terms are there. No, all these terms here are never there. In fact, you cannot even find the last of these terms, ever. So that means if you had immortal life and you could sit down and write down these terms forever, then supposedly you'd sometime reach the sum, which is 1. Nope, that would never happen. And now some idiotic physicists like to say, well, when we go from 0 to 1, we've actually crossed all those distances. But that's total garbage, because we never traverse this distance in this pattern, okay? So for example, we'll go halfway and then another halfway. So we'll do it like this. We'll say half plus a half, or we'll go 3/4 plus a quarter, okay? Or 7/8 plus an eighth, or some other linear combination that gives us 1. But we never, ever find the sum using this method. This geometric series here has a limit of 1, but it can never be 1, okay? Never. So my inferior colleagues in the mainstream decided that they would simply follow Euler's ill-formed definition and say S is equal to lim S, right? Where S is this series, okay, this geometric series, and lim S is the limit. And that's exactly what Euler did, okay? And it's wrong because it's ill-formed. You don't assign a number to a sequence. Now, they were desperately trying to produce a rigorous construction of a real number. They failed miserably, but anyway, and I'll show you now in a moment why they failed. Let me just get rid of that. Okay, so, and I'll come back to this here, but I first need to talk a little bit about Dedekind and Cauchy. Now, Cauchy really worked with convergence sequences or series. By the way, a sequence is derived from a series. So if you had a quarter, a half plus a quarter plus an eighth, like that, then a sequence would be the partial sums, okay? So the first partial sum is a half, the second one is 3/4, the third one is 7/8, etc., okay? So this here is called a sequence, and this here is called a series. And the sequence is derived from the series. Now, and of course, the limit of both of these is 1, so it doesn't matter whether you say it's the limit of the series or the sequence. That is what Cauchy was working with, okay? So And a sequence doesn't necessarily need to be geometric, provided it converges. So for example, this sequence here, which is used to approximate the value of pi, I'm sure that's 3.1, 3.14, etc., 3.141, like that. This sequence here, which can be obtained from a Taylor series expansion or one of many other means, is also a Cauchy sequence, okay? And its supposed limit is pi. Now, it's not known what is pi, because if it's not a rational number, we don't know what it is. And moronic academics like to say, well, an irrational number is one that's not rational. Well, then just about anything I can think of is not rational. A gorilla is not rational. This screen you're watching in front of you is not rational, because none of these things can be expressed as a ratio of two integers, okay? So you never produce a definition that describes an object in terms of attributes it does not possess, okay? It must always be based on attributes that an object possesses. For example, a rational number is a number that has the attribute that it can be expressed as A over B. But what the hell is an irrational number? No, you cannot say not expressed as A over B, because it could be anything in that case. It doesn't even have to be a number. Do you get that, moron? It doesn't have to be a number. And in this case here, it isn't a number, because there isn't any number describing pi, right? So desperate to try and punish, the creators of the universe, who also, incidentally, cannot measure the magnitude pi. Pi is a magnitude that is not commensurate with any other magnitude. And I normally just call it an incommensurable magnitude, okay, which is what I just described, a magnitude that is incommensurate with any other. So we're not able to measure pi. Not even the gods can measure pi, or even square root 2 or e, or any one of those other so-called, falsely so-called irrational numbers, when there isn't any rigorous formulation of an irrational number, okay? So the only thing that you're told about an irrational number is that it's not rational. And that doesn't tell you anything. What the hell is it if it's not a rational number, okay? So apparently it's some magnitude that cannot be measured. And so pi, when it's called a limit here, it's not a limit in terms of a number, because there is no number that describes pi. It's just a certain magnitude, all right? A certain length based on some chosen unit. So this part here is not measurable, okay? So you can measure 3 units, and then there's a certain portion of this little part here which is not measurable. You can carry on like this and get more approximations, etc. But whatever you have over here to any n terms is never pi, okay? This is not equal to pi. And it's folly to write this here is equal to pi, because it's not equal to pi. So for any number of significant digits you can give me, I can show you innumerably many other numbers which have exactly the same n digits in the same places as pi, all right? Now, the baboons in mainstream academia have never stopped to think that in their quest to, in their decree and their quest to say that an infinite decimal expansion expresses any number, they didn't bother to think that if, in the case of pi, you're simply not able to determine it. So it doesn't matter how many partial sums you determine. In this case, what you determine is always a rational number. So it doesn't matter even if you could theoretically sum all these to infinity, you'd always have a rational number. But we can prove that pi is not a rational number, okay? Not rational, all right? So it can be expressed like this, but yet the way the morons express it is 3.14159 ... meaning that that is a unique expression of pi in base 10, right? Which is total garbage. Just like when they say 0.333 in base 10 is equal to a third. It's not, okay? And it's not even unique because I don't care that you can say the 3 doesn't change. They're not all there. And as I showed you early on, because of this term here, you'll never reach the limit, which is a third, okay? So this here is decidedly not equal to a third because of this, right? And there's another theorem also that I showed you earlier, which says that if the denominator does not have prime factors that are 2 or 5 or both, then it cannot be measured in base 10, okay? So Cauchy decided that he was just going to simply say, since we can form different equivalents, since we can form different classes, or a class of equivalent Cauchy sequences, equivalent convergent Cauchy sequences, well, that's actually redundant because all Cauchy sequences converge to a magnitude, okay? Now that magnitude that they converge to may be rational or something like pi or e or square root 2 or square root 5, etc., okay? So now we know that Cauchy's idea was basically to say that the limit, and I don't know why I'm writing it here because I've got it over here, is to say that a number is defined as the limit of an equivalence class of Cauchy sequences, okay? Now there are many problems with this because in the case of a quarter, the limit is the sum, right? So a quarter is simply 2/10 plus 5/100, right? Period. That is 25 or 100, which is 0.25, which is a quarter. But in the case of a third, the limit is not the sum because it doesn't matter how many terms you sum in this series. It doesn't matter. You can sum them forever and you'll never, ever, ever get to 1/3, okay? Because of ARN over 1 minus R, okay? And also because of the fact that this 3 here, is not a prime factor of 10, okay? So the only even the only rational fractions that you can measure are the ones that have the same prime factors as base 10, which are 2 and 5. If the denominator has any other prime factor, it cannot be measured in base 10, except as an approximation. That is, 0.333 is approximately equal to a third, okay? And it doesn't matter how many 3's you add there, it's only approximately equal. It's always less than a third. Now, so the mainstream academics have these 3 rules, which they use with this particular idea of Cauchy sequences. The one is that the limit is the sum. The second one, the limit is not the sum. And the last one, the limit, who knows what the hell the limit is, because it's some formula that we use to determine partial sums of a magnitude that cannot be measured, okay? So they don't even have, this rule here, it's not even a rule. This definition here has 3 variations, okay? It's not all the same. And it doesn't even work, as we see, for example, in the case of a third, and in the case of an incommensurable magnitude, pi, right? Doesn't work. So Cauchy failed to construct a valid object that is a real number. And if you read my article called page 3117, and the reason it's called page 3117 is that I had a very lengthy debate on a site that no longer exists about these topics. And I show you in that article, which is available and I'll place in the details section, that you can create as many sequences as you like, Cauchy sequences, which are equivalent, and yet none of them actually tell you anything about the real number, except that that class of equivalent sequences has the same limit, okay? That's why in the notepad, did I get rid of my notepad? Yeah, that's why in the notepad, not this one, but this one, we say it's the limit, because the limit is what makes these equivalent. Cauchy sequences, okay? If their limit is not the same, then they're not equivalent, and you don't have an equivalence class. An equivalence class is just a set of Cauchy sequences, okay? And what do those Cauchy sequences have in common? They have the limit in common, all right? The same limit. That's why they're equivalent. All right, so Cauchy failed big time. And then the next moron who tried to construct numbers, real numbers, was Dedekind. And now Dedekind's idea was based on that mythical object called a real line. Now, there isn't, you cannot create any instance of a real line, okay? So can you create an instance of a rational number line? Yes, because you can reify rational numbers on the number line. And that's a big topic which I've discussed several times. I'll place some links in the detailed section of what all that means. But you cannot, for example, even say, if you wanted to designate that as pi, let's say you can mark it out as pi, like that, on the number line, you still need a number to describe that measure. So here you've got 1, 2, 3, but what the hell describes this distance here? Nope, you can't say pi, because pi is just a symbol of the magnitude length. A number, by definition, is the measure of that length, okay? And you cannot measure that. There is no number that you can calibrate this number line here so that it can be a real number line. Did you get that, moron? You do not have a real number line. It is a bunch of poppycock. And it's absolutely absurd to say that points on a number line corresponds to numbers. They do not, because a point, first of all, has to be reified. And if you can reify or measure or create an instance of a point on a number line, it doesn't exist, all right? So this point pi here doesn't exist, right? There is no point pi, because you need two things to reify a point. You need to be able to construct not physically necessarily, but you need to be able to construct the magnitude and also a number that corresponds to the measure of that magnitude, okay? So there is no unit that measures pi or square root 2, for example. So in the case of pi, you have a circle like that, and it doesn't matter how big the circle is. Whenever you use the diameter to measure the circumference, you cannot measure it, which means there is no unit that measures this magnitude, this ratio, because pi is truly just a ratio of two magnitudes, okay? The circumference to the diameter. And at least one of them cannot be measured. At least one of these cannot be measured, or both. So anyway, not to spend too much time on that, Dedekind decided he was a genius, or didn't decide, he thought he was a genius. And he said, if that's a particular point, let's say P, then we can define it in terms of all the rationals on this side and all the rationals on the other side. Of course, there is no such thing as an infinite set, so that's total crap, okay? And that's the first point. And the second point is that you can constantly get closer to that point, but there is no rational number on either side which acts as a boundary for these sets, okay? There is no rational number. The only boundary is actually this point, which we are trying to reify, this point P, okay? That's the actual boundary. So in his stupidity, what Dedekind did was create two sets, as we see here like this, which supposedly sandwich this number. So 1 over square root 2 is approximately 0.707. And what he did was he said, okay, first of all, let's just get rid of that. I'm going to show you, if you have a first set with denominators 6, then this is what it looks like. And this set is not a fixed set. It changes, okay? So if you have with more denominators, then you have more rational numbers. So they're not the same set. And in fact, you may say, well, you'd need all of the rational numbers. Well, get a clue, moron. You never have all of the rational numbers, because it's impossible to have all the rational numbers in these sets, okay? And let me show you why. It doesn't matter how big n gets, right? Doesn't matter how big. You can never, ever have the complete set. And all you really care about with respect to a Dedekind cut is the section close to the number, okay? So these parts here, contrary to what morons think, are irrelevant to a Dedekind cut. You can describe the cut simply using a small interval that surrounds it, and ignore the rest of it, because any number in that interval will have the same boundary as far as these are concerned. As far as this interval is concerned, as far as this interval is concerned, well, it doesn't matter, because all that matters is the neighborhood around the point, okay? And as you see, it doesn't help you because the limit as n approaches infinity is not equal to 1 over square root 2. There is no unique m, as I've shown you. M is the division of the two sets, okay, into a left and right. No unique m that will give you the particular number or the particular magnitude that you're trying to measure on the number line. So Dedekind cuts have many flaws. They're complete garbage, and Dedekind also failed to reify so-called incommensurable magnitudes and describe their measure. And for example, set theory is very flawed. So aside from the fact that there is no infinite set, okay, there is no infinite set, that's the first caveat that stops us from looking at Dedekind. And then I've just shown you a lot of others. For example, you know, you can distinguish between the sets, and it doesn't matter that you can do component-wise differences which give you 0. That doesn't describe what real number you're dealing with, okay? It doesn't even give you an idea of the measure of pi. So for example, the fact that you can have two equivalent sequences for pi and the component-wise differences are 0 doesn't tell you anything about the measure of pi or the square root of 2 or any other incommensurable magnitude. Now, some morons think that I use the term incommensurable magnitude and everybody else uses irrational numbers, but the two are not the same, okay? A magnitude is not a number. So anyway, I think I've given you a lot of history and background on how we got this myth of infinite decimal expansion. It doesn't exist, okay? Fallacy, it's not true. You cannot write something down like this. It's nonsense. Just as 0.333 dot 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 is nonsense, just as 2.71828 is nonsense, etc. And I showed you in earlier episodes why you can actually find limits using the properties of rational numbers. So typically in an IB diploma, they'll ask you, or give you a little number, they'll give you any number like, you know, maybe 2.5555 like that, and ask you to convert it to a fraction. And then typically what you do is you multiply it by 10, right? And you'll have 25.555, and then you subtract this one from this one, and you're able to find the fraction that gives you this pattern, okay? When you do the division, that gives you this pattern. Okay, so the fact that you get a repeating pattern when you're dealing with a rational number P over Q is a consequence of the fact that it is a rational number, right? And when you're trying to find an expansion for an incommensurable magnitude like pi, you cannot find a repeating pattern in any radix system, okay? And of course, this here isn't true in every radix system either, because, for example, a third is not measurable in base 10, even though you can say, do something like that and then multiply by 10 and then you end up with x is equal to the third. That's just total garbage, okay? It's not true. And I've created many videos where I've shown you that what you put in there is what you must get out in this process, in this supposed 10x proof, right? Because if you multiply this by 10, like that, object, and then you subtract them, you get 9x, and this will be 9 times object, which means x is equal to object, okay? And so if you put in, whatever you put in there, you must get out. Seems like the morons in mainstream academia are still not aware that you cannot multiply by an infinite series, okay? Multiplication does not distribute over an infinite sequence or series. That's just total garbage, and I also have videos on that. Okay, so now to summarize, this is how you got all your theory on numbers. And in the mainstream academia, they tend to look at numbers as points on the number line, which is total crap, because points on a number line are only reifiable if they exist, right? Which means they need to have a number that describes them. And everything in mainstream mathematics, their entire understanding is based on that mythical object called the real number line, which doesn't exist, which makes no sense, and from which most of their fallacious theories are produced. So I think I've covered a lot on decimal expansions and the myth of infinity. And so in the next video, I'll continue with our history of mathematics. Now, as you'll recall, I started with nothing and brought you up to this point. So I'm going to continue without assuming any prior knowledge. So far, I've shown you from part one how to derive all the concepts, because there are no axioms or postulates in mathematics, and many of the mainstream ideas are just plain rubbish. So I hope you've enjoyed this presentation and that you'll join me again for the next episode sometime in the near future. This is the New Calculus channel. My name is John Gabriel. Till next time, goodbye.